neuron-based AI that is managed by the engineering AI is used for automatic generation of the computing process to resolve the task. And Yevgeny Burnaev is going to talk about the technology of the engineering AI and the applications. Professor, the head of the Applicable AI Center of Skoltech, a senior associate and fellow, and the head of the scientific group called Trainable Intelligence of AIRI, Yevgeny Burnaev. Engineering AI, the scientific foundations for industrial applications. Okay, hi everyone, let's talk about AGI and engineering AI. You know about AI. AI resolves specific tasks. Usually it's based on neural networks, and these are the models that do object detection, classification, or other tasks. Now, the things I'm going to talk about today, this is really not a AGI. This is a step towards that, the creation of AGI, but as I will mention today, it helps and will help to resolve complex engineering tasks. Now let's talk about the details. Not many of you know that in the 1980s, 1990s, a very important place was taken by the symbol-based AI and symbolic AI. And back then they were saying that, okay, the AGI will come soon and all the computers will be using symbolic computing, but in mid-90s everyone forgot about that. So the third generation neural networks appeared and they started to be used for engineering tasks. But people forgot about that before we had this popular paper that you know about. Now, AI is based on the deep neural networks, DNS. But this is an analogy, really. You cannot really say that's a specific term, but you can talk about the AGI as a as something structured, and modern language models serve as kind of an engine for it. Here we're talking about the foundational models that build predictions in different situations, and you can talk a lot about that. It can be kind of something subconscious that can deliver this or that function. And the basic idea is to unite these two worlds, and the symbolic AI, here we're talking about LLMs and generative AI, is managing the process. It orchestrates.
And then the computing itself for the problem solving is based on lower rank approaches. Jumping ahead a little bit, the potential cognitive structure of this approach, it might look like this. First, we need to understand that when we are solving actual engineering problems, it's very important to have industry-specific expertise, domain-specific expertise. Whether it's generative design or designing a manufacturing site facility, some complex engineering mechanism. In each case, we need regulatory documents, normative documents for domain knowledge, which is why we need a knowledge graph, which is a straightforward way to represent the knowledge from this knowledge repository. So there we have this knowledge graph, which describes the domain and its limitations. The person is outside of this system. They set low-level requirements to solve the task. Then the requirements are interpreted by an orchestrator, which takes the knowledge from the knowledge base, relevant knowledge to solve the task, sets constraints with the help of that knowledge. Then the constraints form an optimization problem within which we build computational chains built from specific agents doing specific computation. Then you start the computing chain, and potentially you can repeat this in the second cycle. Obviously, the knowledge graph is different depending on the domain. We need ways to automate its building, but the methodology itself, the library of agents, and this environment in general is the same. Before we begin considering examples, and there are some good examples, good use cases, let's talk about the promising fundamental research which motivates this concept and which also helps explain what we can expect and what are some of the bottlenecks. I am talking about building systems which can solve complex problems. With the problem that I presented earlier, the general engineering problem, you primarily need knowledge from the domain which the orchestrator would be using in its solution. The question of memory arises. What is the environment that you can use for testing? The extent to which orchestrators or other generative agents cannot perform well with memory. The natural answer is text-based games. Many of you probably remember they were popular in the 90s. They're still pretty popular. So you have an environment where you, as the agent, are moving around different spaces, different rooms. Each time you are receiving a textual description of the environment, the textual description of this new room. The problem is that the amount of information you're getting is increasing. The environment varies depending on your actions. And a standard agent based on a language model would fail at it because the amount of context it would need to fit into the memory would be growing exponentially, and it would be getting a lot of rubbish into it. If you apply to this game a standard GPT-4, some state-of-the-art language model in a relatively small number of steps, the model will start underperforming. It's an easy experiment. How do you fix the problem related to language models? An obvious example of how it can be tackled is using modern methods based on RAG or some other methods, pretty straightforward engineering tricks. For example, you could upload the full history into the LLM, but obviously this option will quickly exhaust itself, because even if it's a game with not too much text, the memory will quickly be overwhelmed. Or you can use RAG. It's a bit more simple, but once again, the question of noise. How do you organize bits and pieces of information, these chunks of information that you are preparing after the retrieve from the database? And another method is summarizing. Each time that you're obtaining new data, new textual description about a new room, you are adding it. You summarize it to add it, and the obvious risk is you lose some relevant information. There's been a proposal how you can fix the problem I described. On the one hand, you could use language models without any fine-tuning. It may be relevant to some problems because there might be insufficient training materials, and also the computing power may be insufficient. So the assumption is that a language model must be able to plan and make decisions based on a prompt that is put in. How do you fix the problem I'm talking about? It's all about memory. The memory is organized as this. It is organized as a knowledge graph. A language model, at each step, if we give it a special prompt, can retrieve from the descriptions of the rooms that we are walking in. As an agent, it can retrieve from these descriptions some information. Then this information is represented as a semantic representation. So essentially, it's subject, relation, object. So it's a triple representation with the connections in between the three. And we are using As you can see in the picture, we're using the description of events. So we are walking into a room where there are some items, red apples in this instance. Semantic bits of memory are the different triplets. We can represent connections between different items, and the episodic memory is where we found the red apples. One of the text-based games is you walk around the rooms and you are supposed to collect items, groceries, to fetch them to the kitchen and cook something using a recipe. You must retain the sequence of actions in your memory, and even if you have good memory, it might be challenging sometimes to remember the whole list, and sometimes you pick up just any random items. Imagine what a problem it would be for a language model, which sometimes struggles to scale up depending on the context. So to implement this concept, we need several specific actions. We need to build a semantic memory in a particular way. We are using an LLM with a specific prompt, which helps us retrieve triplets from a text description of a room. The triplet I mentioned, a subject relation object. Then the LLM with a different prompt checks whether there are obsolete triplets, out-of-date triplets in the knowledge base. We get information, retrieve subjects from it. We look at the nodes of the knowledge graph that correspond to it, and we make a decision whether it's out of date or not, whether we remove it from the knowledge graph or not. It is all done on the fly, so it works dynamically. And the final step is the organization of memory. With this approach, with this dynamic approach, you can stockpile the different chunks into the knowledge graph, the necessary information about objects, subjects, and the connections between them. As a result, when the time comes to take another step, to take another action, the LLM behaves like this. It needs to plan something. It receives new information about the current situation. It retrieves the semantic information out of it about the triplets that are present in the description of the room. You do in-depth search using embedding vectors. You look for the right nodes of the graph containing relevant information. And we are talking about a fixed size of the context. You do the same for the episodic side of the memory. You're looking for related events related to the triplets with the observable information. As a result, we can build the knowledge graph on the fly. As I said, this is an example of the game graph, which is called cooking. And this is the structure of the game, how many rooms it have, and this is the graph that you can build on the fly, and it represents pretty well what is happening inside the game. As a result, you have a system. It can, of course, be fine-tuned. It can be additionally trained, but even if you don't, it performs really well. The same LLM with different prompts, with these different retrieve methods to retrieve information from the knowledge graph. The very first chart shows that we have games of different levels of difficulty. You can have games with very few rooms or games with a lot of rooms. So with the games of varying difficulty, we ran an agent that analyzes the full history, the agent that uses RAG, an agent that uses our technology, and a human player. The outcome was we were, on average, better than all of the other methods. The main drawback is that we were slightly behind some of the best players who simply have good natural memory and who had played these games really well before. Comparing it with reinforcement learning, an obvious comparison. This is the diagram. This shows that, once again, we are way ahead of such agents. It shows different levels of difficulty for the cooking environment. It turns out that the score achieved by our agents, the red bar, is much higher than the different RL agents gave. This approach to memory is right, fair, and natural, especially speaking of engineering applications. Why? Because when you want to retrieve from documentation describing specifications for a car, if you want to retrieve the specifications of an engineering device for a child 3 years or younger, it can be located in the text at random places, in different tables. It's very important to represent, it's very convenient to represent this message, this information as a knowledge graph. We also use this, we also try this with Q&A benchmarks, with a Q&A setting. We're only using the part with the memory, so before we answer the question, we take all the documents that are potentially relevant for answering the question. We build the knowledge graph on the fly based on the documents, and the LLM, without any fine-tuning, can answer specific questions guided by the retrieved semantic information from the knowledge graph. I would like to show you this table here. The key point is this. Of course, there are Q&A systems that work with these Q&A benchmarks really well because they have been created to do just that. What I am describing now is just this general method, this general technique, which is not specially fine-tuned for this problem. And still, the quality of the answers we got are comparable, are second to the specially developed method highlighted in the table. I think this is a great result because we didn't have to spend any time on it, any computing power. We just launched it and it worked. Clearly, an assistant like this, with a memory like this, can be really useful for all kinds of personalized tasks, to work with documents, to summarize, using the knowledge graph, and answer questions, retrieve requirements, and all sorts of things. You can say, well, this is a good concept, tried with text games, but what about the engineering problems? A lot of ideas that I work on grow from generalizations of applied tasks. In this case, we are talking about the self-learning reservoir model, a very non-trivial task where we have oil reservoirs of different types, and we have information of different types, seismic data, for example, of varying quality, hydrodynamic dimensions, hydrodynamic data, data from geological surveys and research. So these data, this information is around a specific well, a specific reservoir. We need to build a model of the reservoir that would factor in all these different types of data, because we want to build a model that combines all these types of data to make sure that the estimate of the physical attributes of the reservoir would enable us to forecast the oil production volumes. So we need to continuously fine-tune and adjust this model, a lot of computing steps, because once again there are a lot of different types of data, and we also need to factor in the domain-specific knowledge. A very natural way to tackle this problem is to use the multi-agent system that I described in the beginning. The knowledge graph here is built based on expert knowledge, domain-specific knowledge. We have to interview experts. It's as simple as that. But once we have it, most operations processing the data allows you to build chains of how you can convert one type of data into another. You can do this on the fly. You know what computing operations need to be applied. And each operation is done with so that agent. Agents can be physical models or models based on data. As a result, we implemented this software suite, this software complex. We applied it to a number of deposits, a number of reservoirs, and we got good results, meaning that the time in which the reservoir was built was much smaller, was much shorter than what is customarily needed for engineers for different departments to build. And also accuracy is much higher. All of that is automated. The question is, what about generative models? The generative model is one of the agents that help process multi-model data about the oil reservoirs, because we usually think about generative model as model that generates images of kittens and puppies, but in fact we can apply this to oil and gas and analyze seismic data, geological survey data, it's temporal data, spatial data. So it's a model that needs a lot of adaptation as compared to standard generative models based on division processes. We need to understand that with the oil and gas applications, we, of course, could benefit from multi-agent systems, but they are not the only ones. As I said, what we are developing or we're working on, and what we plan to use as a publicly available toolkit is this approach that helps you solve a variety of tasks, including problems related to engineering and design for manufacturing sites. The situation is similar because you need to simultaneously design a building or a facility, what's inside that building, the wiring and things like that, all accordance with the regulations. You need to position all the things at the building, on the site, utilities, communications. This applied problem is once again solved in the same vein with the same cognitive architecture as I described earlier. We are making progress, and we have already done a great job. We show that you can use information from regulatory documents with restrictions and constraints for design. You can retrieve that information in a reliable manner with the systems that I described earlier.
And actually, if you talk about the information about people in some large systems like banking system or systems from the large IT companies, we're talking about multimodal, diverse information, and it is updating all the time. Some data are removed, some data are added. Very difficult challenge, but a very exciting one that can be resolved with this system. We're talking about large cohorts of individuals with large set of data, transactional data, data on the activities of a user in various online systems, and based on these data, you can build digital twins. So these will be these chains of agents. They are going to build for every person, based on the input information, an avatar. If you have a set of avatars for everyone or for a group of people, because, maybe it will be hard for a system to calculate it for an individual person, then you can model the socio-economic system in a pretty accurate way. It's quite hard to do that, so we have to lay the engineering ground before that. In conclusion, I would like to say that, of course, the LLMs will not be forgotten as quickly as the symbolic AI models. We have LLMs and multimodal models working side by side with us. Now, AI is a kind of a vague term, concept. It's pretty far away from the truth, and what is AGI is also a kind of a vague term. I think that the natural step towards that might seem pretty far-fetched in terms of the fundamental development of the technology, but on the other hand, it is, pretty real in terms of realization. And you will be able to resolve the tasks and problems for general classes, and that's very important with AGI. Now, in my presentation, I tried to talk about the applications where it might be used. This is the link to our paper, the QR code, my contact details. Thank you very much, and if you're interested, please make sure to contact me. Evgeny Burnaev, a round of applause.